The afternoon plenary session, and the first speaker is James Gray, and this is his title.
It is indeed. Okay, so thanks very much to the organisers for the opportunity to speak and for a very nice conference. I'm learning a lot. So I want to talk about various aspects of finding solutions to heterotic theory for phenomenology. So heterotic backgrounds that you would compactify on to get 4D physics that looks like the real world. And the talk is going to be split into essentially two pieces, a non-Calabi-Yau bit and a Calabi-Yau bit. The non-Calabi-Yau bit is based on work with Magdalena Lefors and Dieter Lust, both of whom were in Munich at the time, although Magdalena has now moved to Oxford. And the Calabi-Yau bit is going to be a discussion of aspects of this sort of big program that we have going on with various collaborators. And the stuff I'm going to be talking about is with Lara Anderson, Andre Lucas, and Erin Pouty. And these are the most relevant preprint numbers for what I'm going to say. I guess I can. Yeah. So let me start by talking about compactifying the gravitational sector, if you like, of heterotic in a bit of generality. And what is it we can do to try and get various types of n=1 theory from compactification. So normally what people will do, if they're thinking in geometric compactifications, is they will take heterotic theory, say in 10 dimensions, and they will try and compactify 6 dimensions on a manifold of SU3 structure. And the reason you choose a manifold of SU3 structure often is because on such a manifold there's a sort of a naturally preferred nowhere vanishing spinor, and you can organize how you keep multiplets and so forth for your 4D theory so as to preserve the picked out the preferred n=1 supersymmetry in 4 dimensions that this SU3 structure tells you about. So such manifolds can be classified to some extent by their torsion class. And what's this? So just like a Calabi-Yau, which is in fact a special case, an SU3 structure manifold has 2 nowhere vanishing forms on it, J a 2 form and omega a 3 form. And in general these aren't closed. And the degree to which they're not closed, which is the degree to which this isn't a Calabi-Yau, if you like, is classified by what are called the torsion classes. So we have W1 a function, W4 a 1 form, W3 a 3 form, and so forth. And W1 to W5 are called the torsion classes and tell you basically to what extent you're not on a Calabi-Yau. So it's not good enough to just take any old manifold of SU3 structure and say, hey, I'm going to compactify on that, I'm going to get an n=1 theory in heterotic. Fantastic. You have to make sure that it's going to be a solution to the theory. And exactly what the criteria are on this manifold, in other words, what are the criteria on the torsion classes such that it is a solution to heterotic theory, depends on what exactly you ask of the solution you're looking for. So the first thing you could ask for your solution is that it's as simple as humanly possible. And that leads you to the Calabi-Yau case. So if I set all of the w's here to 0, I have dj=0, d omega 0, closed 2 form and 3 form, and I have the Calabi-Yau case. And that's what I'll talk about in the second part of the talk. This is the only case where, the reason why this is a simpler case to deal with than the others, is this is the only case, if you like, where the methods of algebraic geometry apply at least directly. So the only projective varieties of SU3 structure are Calabi-Yau. So this case is in some sense simple. But you could ask a sort of more physically motivated question of, make more physically motivated demands on your solution than just saying I want it to be simple. One thing you could do is you could say, okay, SU3 structure in some sense is going to give me an n=1 theory, but I want that n=1 theory to have an n=1 vacuum, which is maximally symmetric in 4D spacetime. And this is sometimes called the Strominger system. There's a bunch of criteria essentially on these torsion classes for such a solution to exist. Strominger was working in the 80s and he didn't phrase it in this way, but these authors rephrase this, what the necessary conditions are in the torsion classes for such a solution to exist. And it's that W1 and W2 are 0, and W4 is a half W5, and they're both exact forms. So phi here is the dilaton, because it's D of something, these have to be exact forms. You can see this is quite a constraint on the possible torsion classes, right? Asking for this to be the solution of heterotic theory with these properties is restricting what manifolds we can compactify on, as you would expect. Now you may say, well, it's a restricted set of manifolds, but that's your problem, you have to deal with them. We want an n=1 vacuum with maximal supersymmetry. And to some extent that's true, but you do have to be a bit more careful if you want to do something general. So the point is that what we want is a nearly n=1, nearly Minkowski, say, vacuum, after we've added in all the effects that we use in, say, our moduli stabilization scenario when analyzing one of these models. What this is an n equals 1 perturbative vacuum. But in many of our stabilization scenarios, we try and add in non-perturbative effects. And if you're going to do that, it's not clear that you need a Minkowski vacuum perturbatively. In fact, you may not want one. So you can have something that doesn't give you, say, an n equals 1 vacuum perturbatively, but when you add the non-perturbative effects back in the 4D theory, everything gets fixed up and you can find a perturbative vacuum again. And in some sense, this is a bit like a heterotic version of KKLT. You can imagine having a non-vanishing perturbative superpotential. This causes, in the heterotic case, it would give you a sort of domain wall half BPS vacuum in your 4D theory, perturbatively, and then you add the non-perturbative effects and you try and balance for a vacuum. Of course, this is a hard thing to do. Either the perturbative effects have to be anomalously small, or the non-perturbative effects have to be anomalously large somehow, and there's various ways of doing that in different scenarios. But nevertheless, this is something that we look at all the time, and so it's a case we should consider. So you can ask, if I ask instead for an n equals 1 maximally supersymmetric vacuum, if I keep this sort of thing in mind and I look for something less general, less restrictive, what can I do with my compactification manifold? So Lucas and Matty had a nice paper where they said, well, instead of asking for an n equals 1 vacuum perturbatively, I'm going to ask for an n equals a half vacuum in 4D, a vacuum that only preserves half the supersymmetry and isn't maximally symmetric, but gives you a domain wall solution. And then the idea is you get a 4D theory when you compactify in this space that has this domain wall vacuum perturbatively, you add these other effects in and hope you get something phenomenological. And they did an analysis of what the constraints are on the torsion classes if you do this, and they found that they could relax some of these constraints. And in particular, these are the constraints they found. They look exactly the same, but there's these minuses here. That means the imaginary part. So if I write something plus, I'm talking about a real part. If I write something minus, I'm talking about an imaginary part. So what they found is that you could actually not restrict the real parts in my conventions of these two torsion classes, and they dubbed these manifolds generalized half-flat. It's just a more general set of manifolds. So what am I going to do in this context? Well, with Dieter and Magdalena, one of the things that we can do is, in the previous analysis, the complete set of Never-Schwarz fluxes that were consistent with the symmetries weren't included. It was a subset. So we're going to add in some extra fluxes and see if we can generalize what torsion classes were allowed even further. And the other thing I'm going to do is I'm going to provide an explicit solution for the supergravity fields, in particular in terms of the torsion classes, in particular for things like H. And the reason that this is important is to preserve supersymmetry, you're solving the Killing-Spinner equations. But that's not the only equations you have to solve to make sure that you have a solution to the equations of motion. And in particular, you also have to solve the heterotic Bianchi identity. And for that, you need to know what H is so you can plug it in. Right? And it turns out that the Bianchi identities are very restrictive here, as I think a lot of people in the audience talking to people this week have been seeing. And so this is an important thing to know. Okay, so let's give it a go. So this is my attempt at a picture of the setup. We're going to have four-dimensional space here, of which I don't have branes here. I'm just trying to indicate three-dimensional maximally symmetric slices, which are actually going to end up being either Minkowski or anti-de Sitter. The fourth dimension here is going to be some domain wall direction, which I'll denote by y, in which things can change, things can vary. And the 3D space will have coordinates x alpha. And then fibered over this 4D space, we're going to have some SU3 structure manifold, which obviously can change in the y direction. I've tried to show that here. And that will have coordinates x mu, and I'll group the coordinates on the 7 space where all the interesting stuff is happening, this 6-dimensional space, and this y direction up into one set of coordinates xm, and this is the same setup as Lucas and Matty. So if we're going to solve the Killing-Spinner equations, we of course have to make an ansatz for the metric and the other fields. Here's the ansatz that goes with what I just showed you. So I have my maximally symmetric 3D space, a couple of warp factors, the domain wall direction, our 6 manifold. And I have to so that's the metric, and I have to give ansatzes for the fluxes that go with that. So first of all, I can have a derivative of the dilaton as long as it's not in the direction that's supposed to be, one of the directions that's supposed to be part of this maximally symmetric 3-dimensional space. I can have a flux that lives entirely on the 6D space, that's been included before, but there's a couple of other fluxes I can have as well. So one flux I can have is a flux that lives entirely within this domain wall direction, but which is proportional to the volume form. I'm going to call that F. Another thing you can have is a flux that has 2 indices on the Calabi and one on the domain wall direction. Call that HY. And we're just going to plug all of this into the Killing-Spinner equations and see what we get, asking to preserve n equals a half supersymmetry, and including the Bianchi identity. So as has been found before, the first thing you find is that when you look at some of the components of the Gravitino variation, this thing gets set to be a constant. By rescaling coordinates, you can set it to 0, so I'm just going to forget it in what follows. And I'm going to call theta the six-dimensional exterior derivative of this warp factor. And whenever I write exterior derivatives and so forth, it's going to be in 6D here. So you plug this all in, and you get some equations coming from the Killing spinor equations and things like the Bianchi identity. And this is they. So obviously, there's quite a few equations, but the thing I want you to take away is, for example, they're split into two pieces. There's pieces that don't depend on y derivatives, pieces that do depend on y derivatives, variations in the domain wall direction. So y derivative here is denoted by a prime. The consistency at a fixed y, if you like, equations are just telling you what fluxes you need, for example, to support certain torsion classes as evidenced by d omega, as present in d omega. The flow equations tell you how certain torsion classes and certain fluxes cause domain wall variation. Okay. And this has got our new extra fluxes in it, and of course you have to check that it reduces to previous known cases correctly, and it does. And in particular, one nice thing you can do whenever you have a discussion like this is you can take the case where you turn all the fluxes off and you take the six manifold to be Calabi. If you fiber the six manifold over the domain wall in such a way that you want the theory to be n equals a half like this, you'll find that the 7 manifold is then going to be a manifold of G2 holonomy. So you've got a Calabi fibered over Y to give a manifold of G2 holonomy. And that's the concept of Hitchin flow, and so these equations essentially should reduce to Hitchin flow in that case, and they do. Anyway, you have some equations. You have to solve them. They reduce correctly to what's gone before. Now, how do you solve these? Or at least give an analysis of their solutions. So one thing you could do is take a case where you know a nice basis of forms on your manifold and say expand your flux in that basis of forms. Maybe you got this from T-duality to a case that's on a compactification on a Calabi or something. And then analyze the equations by comparing coefficients of your basis forms. And that's not something we wanted to do when we were doing the analysis here, partly because it's sort of, in some sense, that's case specific. And partly because in the case we were interested in, which I'll mention in a few minutes, we didn't have such a basis of forms, so we couldn't do it. So what we did instead to analyze this was to just split up the fluxes and the y derivatives of the SU3 structure forms in a way that's always available on any SU3 structure manifold. So in particular, you can split up H as something times the real part of omega plus something times the imaginary part of omega, something wedge J, and all the rest. And by making certain conditions on the coefficients, you can make this split up unique. You can do something similar for HY. There's two pieces here because these things are almost complex manifolds, so you can also split up things according to their almost complex index structure. And you can do something similar for the derivatives of the domain wall dependence of the manifold. Now, if you have any particular case where you do know a nice basis of forms on your manifold or something, then you can plug that in and you can easily get these coefficients. And we give that in many examples in the paper. But you can also just do a general analysis of the equations, splitting the equations up using this kind of procedure. When you do that, you get some answer. And I just want to show you some pieces of that. So first of all, let's think about solving the consistency conditions. So these are the ones that didn't involve y derivatives. From that, you get some constraints on the various components inside H, but you also get these two expressions. So this is the type of thing I was promising at the start. If you give me the torsion classes, this just gives you HY, the flux you need to support them. It also gives me constraints on the torsion classes for a solution to exist. For example, we see still already that, as was seen in the other cases, W4 has to be exact if you want there to be a solution, even in this more generalized case. However, looking at this flux, we see that other things have been generalized. So let's, first of all, take the case where we turn off the new fluxes and go back to what was known previously. So if you turn off HY and you turn off F, if you set these two things to 0, all of the rest of this stuff has to be 0. And it's not maybe so obvious from here, but each of these pieces is actually independent. They can't cancel each other. That can be seen by doing this split up that we had here. Because they can't cancel each other, if this is 0, they all have to be 0 independently. So what do we get? we get W1 minus is 0, we get W2 minus is 0, and essentially we get W4 is 2, what is half W5, and of course W4 is d phi. And this is the case we had before. Okay, these are the restrictions on the torsion classes that we had before, as you would expect. The point is that these restrictions simply don't apply if you have these new fluxes, and so you can do something much more general. So in fact, at the same level that the restrictions were derived before, the only restriction that's remaining here is that W4 is exact. Now you have to be careful, the equations are becoming rather complicated, and there may be some very subtle issue that if you have a certain type of SU3 structure manifold, there doesn't exist a certain SU3 structure manifold that has Y dependence that could match certain type of fluxes or something. But nevertheless, at the same level which these constraints on the torsion classes were given before, the only thing left is W4 is exact. So you have to go on and give an analysis of the solution of all the equations. Solving the flow equations completes the solution to H in some sense. So for example, in terms of the Y derivative of the dilaton, some torsion classes, and this is some Y dependence of the omega field. And you also get to see how the Y dependence along the domain wall is sourced by the various torsion classes and also by the fluxes you put in. So for example, the flux in the domain wall direction sources a change Y dependence in the 3 form of the SU3 structure. We provide all this explicitly. So as I've said, what we've done is we've generalized the torsion classes that you can include in looking for these solutions, and we've given these expressions for H which allow you to quickly check the Bianchi identities, and then the rest of the paper is just going for a huge number of examples. Well, a large number of examples. So the first type of examples we looked at, well, the first non-trivial type of example we looked at is putting flux on a Calabi-Yau. This is something that was first done by Andre and Cyril. They put flux on a Calabi-Yau, but the harmonic flux, not sort of a non-standard embedding flux, and allow the back reaction of this flux to just completely go into the domain wall direction. So even though there's flux on it, it still remains a Calabi-Yau manifold. So you can try and analyze these types of things. Cosets. And the one we were really interested in is Dieter and Magdalena, together with Dimitris Simpis, had these explicit expressions for SU3 structures on smooth compact toric varieties in 3 dimensions. And we wanted to see if we could find heterotic solutions to those. This is actually why we ended up trying to generalize things, because they didn't solve the Killing spinor equations at first, and we needed to go to a generalization. The sad thing is even though we can solve the Killing spinor equations on these things, we cannot solve the Bianchi identity still in the examples we have. I suspect that's because we don't have enough control over the possible perturbations to these SU3 structures. Even though we can explicitly write down the metric, it's so large it's difficult to deal with. It'd be interesting to either generalize, allow sources on the Bianchi identity or try and generalize that analysis, but things get big quick. Okay, so generalization of torsion classes, some expressions for stuff that's useful. That's the sort of non-Calabi-Yau part of the talk. And instead of talking about some of the examples, I'm going to go on and talk a little bit about Calabi-Yaus instead. Please.
Between what kind of asymptotic spaces are you interpolating with this?
That's a very good question. Of course, it will depend on the case, because the Y dependence is determined by what torsion classes and what fluxes are present. The reason it's a very good question is one of the things you have to check is that, for example, say one of the things is the overall scale of the manifold, right? You don't want that running to 0 somewhere along the domain wall direction. This is bad, right? The reason that's not necessarily a problem is, remember, physically the reason we want to do this is we want to add all these other effects into the 4D theory and end up with a Minkowski vacuum where things don't run. So even though you could have a 4D theory where if you just perturbatively solve and find the vacuum, that vacuum is only valid in certain ranges, when you've added all these other effects in, it would look much more normal, and that would be the type of thing you're trying to do. But the actual Y dependence is case dependent. Yeah. Any more for any more? Okay. So we don't have any examples where we get the maximally symmetric space out. All we've done is analyze the perturbative vacuum. The domain world volume itself will be ADS in any case that the flux F, this thing in the world volume, is turned on, otherwise it will be Minkowski. Of course, actually finding one of these 4D vacuums is hard because you have to find a case where you can tune the perturbative thing small. So that's something for another day. Okay, so I'm just going to say a few words about Calabi-Yau. Fortunately, I'm not going to have to say much about this because in the talk right following this one, Lara Anderson is going to talk about moduli stabilization in our Calabi-Yau program. That's work with Andre Lucas and Bert Overath, and seeing as she's going to talk right after this, I'm not going to say anything about it at all. But we also have this program of model building in Calabi-Yau manifolds. This is the work I mentioned with Lara and Andre and Aaron Pauty. I just want to say a few sort of 10-dimensional geometrical things, if you like, about that. I'm not going to go into any detail on the phenomenology because on Friday, Andre will give a talk going in detail about the 4D physics and the phenomenology of this kind of construction. But I just want to say something about the backgrounds we're using and how they're related to more general backgrounds in Calabi compactification. Okay, so I'm going to talk a little bit about split heterotic standard models. So let me start by saying what I mean by that. So the traditional approach to model building on a smooth Calabi manifold in heterotic is to write down some irreducible rank 3, 4, or 5 vector bundle with a structure group SUN, where n is the rank. And the reason you do this is you can take the initial E8 gauge group. There's some maximal subgroup, for example, of SU5 times SU5. So if you have some nice SU5 valued gauge fields, the gauge group you'll see in 4 dimensions is just the commutant of those gauge field vevs, and you just end up with some nice SU5 group in 4 dimensions, which you can then go on to break further and so forth. The usual story. The point is this is not the only thing you can do. One of the first papers that I was aware of, for example, was a paper by Ralph and his collaborators saying, well, you can also just do something with a more split bundle from a model building perspective. So what you can do, instead of taking an irreducible bundle, you can take a reducible bundle, something that's just a sum of separate pieces, where the structure group, instead of being something simple like SU5, is S of UN1 times UN2 times UN3, and so forth. So for example, I could take E8, great, thanks man, contain a subgroup of E8, not maximal, but a subgroup of E8 is SU5 times S of U3 times U2. This thing's just living inside here. And when you work out if your gauge field vevs are living in here, if you work out the commutant inside E8, you've still got the SU5, of course, nothing's happened to that, but there's also the diagonal U1 here. And you get a gauge group in 4 dimensions naively that's SU5 times U1. So you may say, well, that's no good because, okay, I've got my gut group, but then I've got an extra U1. Some people might want U1, some people might not. The point is that this U1 is frequently not there whether you want it or not, of course, because of the Green-Schwarz mechanism. And so this can be just as good a way of getting towards heterotic phenomenology as dealing with an irreducible bundle. In some ways it can be better. The extreme case of this, of course, is where you just split the bundle up completely and just have a sum of abelian objects, a sum of line bundles. The structure group becomes S of U1 to the n. And this, for example, would give rise to, in the case I'm giving here, if I split up this bundle completely into U1s, I would just have an extra 4 U1s in 4D theory, which I would then have to check a Green-Schwarz massive, and Andre will go through all this. Why would you do this? I mean, why not just, for years we've done this sort of thing, and we've written papers where you try and analyze these types of models. Why would you go to these simpler cases? Well, one, it's about backgrounds again, really. Well, one way of thinking about it. So just like for the SU3 structure manifolds, it's not good enough to say you have a bundle. You have to make sure it solves the equations of motion, and that's turned into certain algebraic conditions. So in all of these 3 cases I've shown you, first of all, the vector bundle has to be holomorphic. That's something easy to check, and I'm not going to mention it more. You also have to check anomaly cancellation. This is some integrability condition on the heterotic Bianchi identity for the Never-Schwarz flux. And this is just checking some topological integers. If you have enough control over your construction, this is again easy to do. The hard bit about checking whether a bundle corresponds to a solution to heterotic theory is stability criteria. So for example, in the case of an irreducible vector bundle, the standard way of doing something, the remaining conditions to solve for the Gaugino variation equations, apart from this one, and this thing comes from somewhere else, is that your vector bundle is what's called slope stable and has slope 0. So slope 0 is just some easy criterion on the Kähler moduli. I'm going to forget that again. The difficult bit is proving that V is stable. This is some algebraic constraint on V where you look at all of its substructure. You have to look at all the subsheaves of V and check their slope versus the slope of V itself. And they all have to obey an inequality, and if they do, it's stable, and if they don't, it's not. And seeing as there's an infinite number of subsheaves, that's in general tough. In general, there could be an infinite number of subsheaves. That's a hard thing to check. How does this change when you go to these other cases, these reducible cases? Well, when you go to the case that's reducible but not fully split up, you look like you've made matters worse. So this criterion changes from V being stable to the sum, Vi, being what's called slope polystable, and again we have this slope 0 condition. Slope polystable just means each individual piece must be slope stable, it must be stable, and each piece has to also have the same slope. So you're doing the same calculation essentially on each piece as you did for V. And that sounds like you've made the problem worse, because instead of checking the stability of one thing, I have to check the stability of a bunch. And you think, well, I just broke it. I shouldn't have done that. But in fact, this can be easier because each of these pieces is smaller, so it has less substructure. So even though you have to check the stability of more objects, it becomes easier because each object itself is simpler. And the obvious sort of limit of this is if you split it up completely into line bundles have no substructure of this type. And so the only thing that you have to check if you split the thing up completely into a sum of line bundles is that some trivial conditions on the Kähler moduli are satisfied. It's not so trivial if you're doing a large number of cases, but nevertheless, compared to this, it's trivial. And so you can generate a huge number of these compactifications and show that they're stable if you go to this simpler case, and they can still have good phenomenology. Great, thanks, man. Okay, I should say, of course, you also have to add Wilson lines to this scenario to break your gut groups down to the standard model. The manifold construction that we work on, the complete intersections in products of projective spaces, doesn't have, each of the manifolds has a vanishing pi1 initially, so you have to quotient the manifolds to be able to put Wilson lines on them. And seeing as you're quotienting the manifold by some freely acting group to get something you can put Wilson lines on, you have to make sure that the bundle also respects that symmetry that you're quotienting by. And that's the subject of equivariance. And I can see I'm going to run out of time, but anyway. So punchline, and Andre's going to go into this in a huge amount of detail, in an initial scan which is now being expanded with various people, the original collaborators and Andre Constantine immediately come to mind. The initial scan that we did in the papers on the first slide, we scanned over about 10 to the 13 different bundles, roughly speaking, and we found 2,122 heterotic standard models. And that's a big improvement on what goes before because you've got this simplification to help you out. And Andre's going to talk all about the phenomenology of these on Friday. What I wanted to say in my remaining 2 minutes is just something a bit about the relationship of these backgrounds to other heterotic backgrounds, in particular to these more irreducible things that we saw before. So first of all, one way in which these split bundles can be related to the more general configurations is that there can be moduli that you turn on that just mix the line bundles back together again. Okay. So this is something we explored from attendant, and lots of people have looked at. Lara and Bert and I had a paper exploring this in these types of contexts. From attendee point of view, I'm sure Andre is going to talk about this from a 4D point of view on Friday. It's about giving vevs to things and Higgsing stuff in 4 dimensions, essentially. I'm not going to talk about that anymore. What I wanted to mention was that there's a fun other way in which these compactifications can be related to more general things. It is not true that because a bundle is a sum of line bundles before you quotient, that it is still a sum of line bundles after you quotient. Right? So you can have something that before you quotient the Calabi is a sum of line bundles, and if each bundle is equivariant individually, it respects the symmetry individually, when you look downstairs on your quotiented manifold, that will still be a sum of line bundles. However, if the sum of line bundles respects the symmetry, but somehow the way in which it respects the symmetry mixes up all these different pieces, then when you look downstairs, you'll find that you have an irreducible vector bundle, despite the fact that before you quotiented it was built out of a billion pieces. This means that you would think that you could have the power of doing calculations with a billion objects on the covering space, but still be investigating an essentially general configuration on the 4D space and on the quotient manifold, and that's to some extent true. So I'm running out of time, and Miriam's told me she was told to be tough. 1 minute, yep. So I was going to give you a simple argument for why, how you can see in a simple case that this can happen. I'm going to skip that and just mention very quickly that this kind of distinction, these kinds of relations can be important for phenomenology. So Andre is going to tell you about how you can grow things back with singlet vevs. But what I wanted to mention is if you have one of these line bundle standard models, which is completely split, is this abelian locus where downstairs the model is just the sum of abelian gauge fields, then you can show that it's not possible to have rank 1 Yukawa couplings at high energy, which may be something you want. So you can't just have a top Yukawa and nothing else at high energy. Just the way the mathematics and the group theory works out, I'll just wave at that for people who already know, but just to say, for the way the mathematics and the group theory works out, you cannot achieve that in the pure line bundle case, and you may regard that as a problem. And the fixes to this problem, if it comes up, is to go precisely to these ways in which these bundles are related to more general configurations. You can recombine bundles, which in 4 dimensions looks like some Froggatt-Nielsen regrowing. But if you work with one of these bundles that's simply not a sum of line bundles downstairs, you may expect the problem doesn't arise, and indeed it doesn't. And the reason for that is essentially because of the way in which these line bundles get mixed together by the symmetry action. When you calculate the Yukawa coupling, the same symmetry concerns that made the rank 1 Yukawa couplings impossible don't exist. So I've gone through that very quickly, but it's because I'm running out of time. So just to summarize, we looked at two types of things, some SU3 structure backgrounds and some SU3 holonomy backgrounds. In the first case, we added some extra fluxes and showed how to find some torsion classes, some generalized constraints on the torsion classes for heterotic backgrounds of certain types, gave explicit solutions to supergravity fields. And for the SU3 holonomy backgrounds, I just discussed a little bit of this program that's going to be discussed by other people at the conference. In particular, the simplifications that can be achieved by using split bundles. I mentioned a number of standard models we've found and how these things, their relationship to more general bundles can be important. Okay, I better stop there. Thank you.
Questions? Yeah.
That story of the line bundles which are in the sum in the covering space and then they become mixed up is very similar to the monodromies that one has in F theory, right? So when you go around the cycle, you are swapping.
It's very similar, and you see in F theory, you see these similar things with problems with rank 1 Yukawas.
Yeah, exactly. So exactly. Like formally very analogous.
Yeah, very, very similar.
Yes, Bobby?
At least in four-dimensional bundle theory, gauge theory, Donaldson theory, split bundles, bundles which are reduced to sums of line bundles are actually singular things.
No. I mean, you can have a sum of a Boolean gauge field that isn't singular, right? There's nothing singular about going to a split point in one of these things. And in fact, you can follow it directly through.
So they're not fixed points of the gauge symmetry action?
No. I mean, so for example, the only way you would get something singular out of one of these things, if you had a bundle upstairs that wasn't equivariant with respect to your symmetry, and then you tried to divide, that would be one way you could get something singular. And for example, Bert's been looking at that with various people, but there's nothing singular about one of these split points. And in fact, it's just, you can tune to that point in bundle moduli space, and you get something called a stability wall, and these things have been examined in quite some detail. Yeah.
Just one follow-up comment. I think what Bobby might be remembering is that if you talk about the moduli space of bundles on Flaviaus, if you're talking about purely stable bundles, then from the point of view of that moduli space, semi-stable objects are singular points. But really, for the physics that we want to do, we actually want to consider the moduli space of semi-stable objects. And if you do the appropriate compactification of that moduli space, get quotients, there's nothing special about these things.
Yeah. That's something called S-equivalence classes, and you actually see an exact mathematicians already had a way to deal with these, and that would, their discussion has an exact mirror in the field theory when you examine it, and as you would expect because you're studying the same equations. Right?
Okay. Any other questions?
Just a comment. I say that the singularity moduli space means that you have some massless degrees of freedom, which are these charged fields that get
okay. So it depends, right? If you include the U1, if you integrated out a U1, which then became massless, then that would be singular. I would write down the 4D theory with those U1s in them anyway, because if you work out the Green-Schwarz mass in the range of epsilon s and epsilon r where they're valid, then they should still be included in the 4D theory, and then it wouldn't be a singularity. But yeah.
Could I just ask? I'm sorry to. Okay, Frank.
When you say you have 2,000 something standard model constructions, do you mean just the standard model group, no extra U1s, 3 families?
Well, Andre will give the exact data of this. So what it means is it's the exact standard model group. If you look at the, there can be extra U1s. In many of the cases there isn't, and Andre will give the numbers. And in addition, the spectrum, which is really what we're talking about, the spectrum that is charged under the standard model gauge group is exactly that of the standard model, with the exception that some models have 1 Higgs pair, some models have 2 Higgs pair, and I think some models have 3 Higgs pair. And Andre will give, I'm sure, tables with all of this data in there.
Since I won't be here on Friday, would you also say the coupling Yukawas and all that work out from there?
So we discuss, I don't want to take away too much from
Sorry,
Andre. So the way we discuss the Yukawas is, because there's these U1s here, as in many other constructions, there's these low energy sort of U1 remnants in some sense that constrain the couplings. And what we give, thanks to code by Erin, is the Yukawa couplings as a function of those singlets, under the assumption that everything is possible by gauge invariances there. And that's in a big database that's available online, and there's a link to it for all of the models from the paper. You could also, the technology exists to calculate the prefactors in each case, but because that's some big Grosvenor basis computation in each case, we haven't done that. But for any given model, you can pick out the model and calculate the prefactors in Yukawa coupling as well. But it's a super potential Yukawa couplings, and physical ones get harder.
This may be related to the comment. So, did I understand you don't have perturbative tau, so you go to introducing singulars a la Rogan-Nielsen?
You mean if you want to get a rank 1 Yukawa coupling?
Right.
So, if you want to get a rank 1 Yukawa coupling, as I said, you've got two choices. You can either have a recombination and grow it back for Robert-Nielsen style, as you said, or you can just take one of these models where upstairs everything's in some line bundles and downstairs it's not. I should say that so far in the scans we've done, although these are being expanded now, we haven't included in the results cases that do reduce in that second way, because every case that we found so far has had Higgs triplets, which is one of the things we throw away. But it is nevertheless a possibility, and in a larger data set we expect it to come about.
So maybe we should thank James
Thank
for
you.
the